Hey guys, welcome back. So in the last videos, we talked all about redox reactions and the activities of metals, and we're now going to talk about making this into a battery somehow. So I really like this topic. Part of me wanted to be a battery engineer for a while, but I didn't go that route for a whole bunch of reasons. However, I still really appreciate battery chemistry because I think batteries will be really helpful in creating a sustainable future that does not have a... Do you want to say hi? Guys, this is my roommate, Brad, doing laundry. Um, so, yeah, I think it's really important in creating a sustainable future because then we could save the energy that we're making. So, like, when I eventually build my own house, which it's gonna be a while, I plan on having like solar panels where I can save energy when it's cloudy out with nice batteries so that, when it's cloudy, I still have electricity. It's just stored in batteries. If it wasn't for batteries, then I couldn't just solely rely on necessarily solar panel to live. So I'm sure you will learn all about my grandeur building an off-grid house at some point, because you know how much I love talking about myself. But let's just get right into the coolness that is batteries. Okay, so there's a whole bunch of different batteries that I'm going to try to make at some point. I'm going to try to make potentially a lemon battery and a potato battery. And I'm not going to try to make an actual like AA battery, but this is what the materials inside look like. I'm not going to explain it too much, but in case you were wondering, this is the breakdown of the inside of a battery. Okay, so the first battery, the voltaic pile, was invented by Alessandro Volta, which makes sense because that's where the word or term voltage comes from when you're talking about electricity. So Volta was the first guy who published his experiments in the 1800s about... My roommate was just trying to slide by on the floor so you wouldn't see him, but little does he know that the camera is not on me at the moment. So, going back to what I was saying. So, Volta was the one who made the first battery, and hence why voltage is named after him. Okay, so here is a very rudimentary battery where you have one electrode and you have another electrode. And there's a voltmeter, so you could just hook something up here where you would have the electricity go through. For our purposes, we're hooking up a voltmeter, which reads essentially what the power difference is between the two electrodes. And then you have the salt bridge, and we're going to talk about all of the different parts of this battery and why it's important. So, if you don't already have the notes that I have that go along with this page open, I would like you to draw this somewhere for yourself because there's going to be a lot after I have gone through the slide. And you need to know all of it, so you need to write it down somewhere. Okay, so let's start from the top. Is this an electrochemical cell, or is it a voltaic cell? And it is a voltaic cell. A voltaic cell, aka a battery, is a spontaneous redox reaction that converts chemical energy to electrical energy. So the chemical energy is between, the difference in activity of the zinc and the copper electrode. And then from that, you're going to make electricity. The electrons are going to go through the wire to the voltmeter. So this is a battery, effectively. And let's see what else we can label. So there's our zinc solid, there is our copper solid, and at this point you might be saying, Ms. West, based on the activity series, we have two solids here. How exactly is that going to work? Well, you also have the solids in solution. So this zinc electrode is in zinc sulfate solution, and the copper electrode is in a copper sulfate solution. So there's both in ion form and in solid form. So it kind of takes care of that, and we don't have to worry about not having the right one as a solid and the right one as an ion. Okay? So zinc, we know, likes to be oxidized because zinc is higher up on our oxidation, on our activity series than the copper, which is right here. So again, there's the solid and ion version of both. So we're just going to give both of them the benefit of the doubt and say, you're the solid and you are the ion. So zinc, because it's higher up, is going to be oxidized, and copper, because it's lower down, is going to be reduced. So electrons are going to go from the zinc, who's being oxidized, through the wire, and as a result, you are going to be left with zinc ions, because when zinc loses electrons, it is going to form the positive ion. So there's the electrons going up, and it likes to lose 2 electrons to form a zinc positive 2 ion. So the oxidation half reaction, you're going to have zinc solid neutral, and because it's oxidized, you're writing the electrons on the product side. So your zinc is losing 2 electrons, forming the ion in solution, and its electrochemical potential is positive 0.76. And all that means is that because it's positive, electrons are going to want to go away from this side toward the other side. And they do. So here you see the electrons going up away from the zinc that's being oxidized through the wire towards the copper metal. So now the copper is being reduced, but it's not the solid copper that's being reduced. It's actually the electrons are going to go onto the wire, and they're going to attract the copper ions that are already in the half cell. So the ions are going to come toward the wire, and they're going to be like, ooh, electrons, I'll take some of that. I like being reduced because I'm a low activity metal. And they're going to take the electrons, and they're going to come out of solution and form the solid right on top of this electrode. So there's the 2 electrons, there are the ions attracting it, and then boom, it makes copper solid, which is copper neutral. Something that you'll notice is like the bottom of this electrode is a little bit wider. That's because this electrode has made more copper solid for the amount of time that the battery has been running. And you'll notice on the other side, there's a skinnier bottom because the zinc solid, which before I'm assuming it was this whole thing was zinc solid, the zinc solid has been going into ion form. So you've been losing solid zinc into the solution. Where here, your solution is now forming into the solid on the bottom. So you're forming more copper metal here. So because on this side you're gaining electrons, we can write a reduction half reaction. So your copper 2 plus will be gaining 2 electrons to form copper neutral. And our electrochemical potential is going to be lower than from the other side, because again, the zinc is the side that wants to be oxidized, so it's going to have a higher chemical potential energy than the copper. Okay, so electrode-wise, this is where the oxidation is happening for zinc. And because oxidation is happening at that electrode is called the anode. So wherever oxidation is happening, that is the anode side. A cute little way you can remember it is anox. So wherever oxidation is happening, there's anox, and that's where the anode is. The anode has a negative charge. Now you might be feeling like, well, electrons are leaving, so why does it have a negative charge? It's considered to have a negative charge because that is where the supply of electrons are coming from. So when you start off at the beginning, this is considered like the source of electrons, so this is the negative side. Overall, this side, the anode, is going to lose mass, as I said before. It's getting skinnier as the reaction goes on because your solid zinc is turning into ions. On the other side, we have the reduction electrode, and that is called the red cat. It's called the cathode. So it's always wherever reduction is happening, that is the cathode. So red cat is an easy way to remember it, just like anox for the other electrode. And obviously, if this side is negative, it's supplying the electrons. The other side is positive because it's considered to be electron missing at the start. You have more electrons on the other side. So it is going to gain in mass because, again, you have the ions forming the solid copper on the bottom. And overall, we have a net ionic reaction. So again, we already know how to do this. We just add the two half reactions. They're losing the same amount of electrons that's being gained. So everything just on the left side of the arrows were added together, which is zinc solid and copper ion forming zinc ion and copper solid. So the salt bridge. The salt bridge is a very important part of this. It is full of an electrolyte solution. An electrolyte, remember like Gatorade has electrolytes, they brag about it all the time, is nothing fancy. It just means that there's salt in it. So all the salt bridge is doing, it has salt and like some water solution. And it's just supplying whatever ions are being used up. So like in the case of this side, the copper positive ion is forming a solid copper. So to keep it so that there's no like buildup of charge on either side, you're going to have positive ions flowing out of this side to resupply those positive ions here. And you're going to have negative ions flowing out of this side to balance out the positive zinc ions that you're creating. So here they said your sodium sulfate is the solution, and there's a flow of positive and negative ions. So again, like I said, the negative ions go that way, and then the positive ions are going that way. Overall, it looks like our battery is running 1.10 volts. So it's working because it's a positive voltage. Very nice. And I think that was everything you need to know for this slide. So make sure that you have all that written down. I know, it's a lot. But, you know, with some practice, it's gonna be super easy. You're gonna be like, oh yeah, that's the anode, that's the cathode. I mean, we've already learned most of it. We know how to determine what's being oxidized and what's being reduced. We're just adding some terminology like anode and cathode and breaking down what's actually happening in each half cell so that we can get the overall reaction. But we already know how to do all that. So really the only thing that's new is some terminology and seeing the electrons flow and the salt bridge.